So welcome to the lecture that everybody has been waiting for, the one that I wasn't even sure I would give. Quantum groups has been a very fun subject to learn about, I must say, especially because it helped address a couple of issues I ran into when I was preparing my lecture on representation theory. Because if you happen to have followed that lecture, you might have noticed that we've actually left out a couple of things that we can do with representations. We've discussed, I guess, in some depth, the possibility of taking like direct sums. So like whatever you call rho plus rho prime or something. You can take images and kernels. And we were able to speak about submodules, quotient modules, and stuff like that. And quotients. So the whole thing of taking co-kernels and stuff like that was also possible. And yeah, like usually you would expect us to be able to take tensor products, or at least that's what you usually learn in a course about group theory. So that is one of the missing pieces we're going to address today. Just one small addition, I guess. Note that what we called our homomorphisms or morphisms of R modules, that this thing is an abelian group always. Under addition, because you can add linear maps essentially, and when they are sort of intertwining maps, their sum is still an intertwining map. And the composition is biadditive, meaning that like f plus g composed with h plus I is equal to f composed with h plus g composed with h plus f composed with I plus f composed with g composed with I. So additive in sort of both arguments. And this all makes the category of R modules or of representations of the algebra R into an abelian category. Which I guess is a nice concept because you can do all different stuff with exact sequences, cohomology, whatever. But like it's not everything we've learned about representations, right? So this means that somehow we need more things, or we want more constructions. If in particular we have nice rings R, for example, as we discussed, like the group algebra for group, or I don't know, when you're dealing with some topological group or Lie group, then that might be a different group algebra. Or if we're dealing with like the universal enveloping algebra of a Lie algebra. And therefore, like equivalently looking at representations, continuous representations or smooth representations of that group or of that Lie algebra. So when I sort of tried to figure out this formalism, I naturally also wanted to look at what happens with tensor products. And well, in our lecture on tensor products, we discussed a lot about tensor products of vector spaces, but really nothing about tensor products of more general R modules. And the reason is that, well, it becomes a bit harder, obviously. And as soon as our rings stop being commutative, it gets a whole lot more difficult. So if you want to do things purely module theoretically, then you have the following construction. If M is a right R module and N is a left R module, where R is some usually non-commutative ring, then we can form the tensor product M tensor N taken over R. But this thing now is not an R module. This thing is just an abelian group. Reason being, what this thing means is that when like small m and small n are elements of big M and big N, and I guess small r is a number, then this structure only allows us to write down like this relation. Sort of, it doesn't matter if you multiply this thing on the right with an element or this thing on the left, because this is sort of what we quotient by when we take the tensor product. But note that even this way, we have no way of writing something like this, because, well, M is not a left anything module. Of course, there exists like a generalization. If M is a right R module and also a left module over some other ring, and N is also a left R module, then this tensor product would be a left module over that other ring. But in any case, this really doesn't help for what we are trying to achieve, because like a priori, everything is like a left R module, or everything is like a right R module. So there's no way of converting this left module structure into a right module structure. Well, I guess with some caveat, but let's not get into that. So we can't really use that structure. But one thing we could do is we could pursue a slightly different strategy. Firstly, note that since R is supposed to be an algebra over C, like everything that is an R module is also a vector space over C. So like we can treat them as vector spaces. So for example, what if we consider M tensored over C with N just as vector spaces? We can take the tensor product and then don't consider it. We consider this. And well, we've just established that we can't really hope to put an R module structure onto it, but maybe we can do something slightly different. Maybe we can first go for a structure over, module structure of a slightly bigger ring, namely R tensor R over C as an module where we can just take the left multiplication. We can just define it this way. Just say that the left thing acts on the left thing and the right thing acts on the right thing. So then you have Rm tensor R prime n. And yeah, you can go through all of the gymnastics to see that, yes, this is a valid definition for a module structure. This is valid. So, okay, we've constructed some kind of tensor product of our modules. And while we weren't quite able to make them into sort of a representation of R itself, we went for the next best thing and said, okay, well, it's a representation of R tensor R. So now the idea is that maybe we can find some way, maybe not for every ring, but like for a large group or a large class of rings anyway, to also make that into an R structure, an R module. So idea, if we were able to find a ring homomorphism, Jesus. And this is really a general thing. If we have a ring homomorphism from A to B, then we can sort of pull back every module over B to also be a module of A. And how do we do that? Well, if A is an element of A, then we can define the multiplication just by saying that, well, we apply F to A, we get an element of B, and then we multiply that with our element of M, where we're using here just the B module structure. So going back to what we were doing before, do we maybe have a ring homomorphism from R to R tensor R for C? And well, it's not clear that we do, but if we do, we can just do that construction. So yeah, fix such a homomorphism called delta. Fix such a hom delta and define a element of our ring times M tensor N, define that to be this thing. And in that way, we have described an R module structure on M tensor N. An R module. So now comes the part where we ask, well, surely this doesn't work for just any homomorphism, or like, maybe it does, but like it doesn't give us the kind of tensor product that we really want. So what does delta have to satisfy for our things, our structure to behave as we would expect? And well, I guess one elementary thing we would always like to have is that if we have not 2 but 3 R modules, L, M, and N, then we want sort of brackets not to matter. We want this tensor product to be associative, well, at least up to some canonical map. And I mean, sure, as vector spaces, this just works, but who says that the mapping L tensor M tensor N to L tensor M tensor N, that this is actually a morphism of R modules. So who says that it satisfies, or that it, sorry, that it still retains the action of our ring? And well, we can, what does it mean for this thing to be an R morphism? Well, this means, so check, I guess. If we multiply this thing by some scalar element of R, we want that to sort of be the same as doing it afterwards. Jesus, really doesn't. Yeah, I guess that is the question. If we multiply with A first, does this really map to the same as if we multiplied with A after applying our map, this map here? And yeah, it's a bit of calculation, but ultimately it shows that if applying delta tensor with the identity after delta, that should be the same as applying identity tensor with delta after delta.
I am still very confused as to what delta exactly is.
Delta, that is some ring homomorphism that we fixed. Some ring homomorphism.
So it's
mapping from R to R tensor R.
Yeah, so why are there three of them then? It should just be one, right? Because you take R tensor R and you map it to just R, right?
No, we map R to R tensor R.
Okay.
So when you sort of apply delta once, you get something in R tensor R, and then you can apply a map that maps from R and another map which maps from R.
I see. Yeah.
And well, this map, this sort of rule that I've just derived here, this really doesn't look beautiful, I suppose. You can also write it this way. So we're mapping once with delta, and then you can apply either delta tensor ID, or you can apply ID tensor delta. And then you have R tensor R in the first component tensored with R, or you can have R tensored with, and then R tensor R in the second component. And then the rule says that those two should be related via the associator, so to speak, so via this map here. And yeah, I don't know if I should mention this already, but note a kind of symmetry here. If we were to write down the rule for associativity of our multiplication, then we would have something like R tensor R, associated one way. Then we apply multiplication to the first component, identity to the second one. Same way we could apply multiplication to the second component, identity to the first one. Then we get something in R tensor R. And then we multiply again And then we get something in R. And again, that should commute. So this is if mu is multiplication. This is just the law of associativity. And well, in that vein, because this diagram here has everything, all of the arrows reversed, we call this the co-associativity. Of delta, and yes, we indeed call delta the co-multiplication. Okay, but this is really not everything, because, well, tensor products, they not only involve some sort of combining vector spaces, there's also some kind of unit, because you can tensor a C vector space with C and, well, not change anything. And since, like, from the beginning on, everything has just been tensoring over C, like C should still be our unit. And that means we need to have some kind of R module structure on C. C needs to be an R module. And how do we achieve that? Well, the easiest way, especially because C is also a subset of R, is to have a ring homomorphism. So we also need a ring homomorphism epsilon. Epsilon from R to C. And again, you can, sorry, not yet. And what does that exactly satisfy? Well, we want C tensor R to be isomorphic to R as R modules. So something like C tensor M, sorry, for any module M, really. If we map this just to C times M, that should actually be a morphism of R modules. Meaning that we need to map A times C tensor M to A times Cm. But this is just delta A applied to Cm. And do I have anything there? Well, in any case, basically that we want this gives us another few identities, another few rules, so to speak, namely that yeah, I guess I just write it as a diagram. That this thing commutes, and The same way we could also do it the other way around. Could do identity times epsilon and then have tensor C. And those two maps here just map C tensor R to CR, and here are tensor C to CR.
Like, I get that the diagram must commute, but what's the implication of all this?
Well, it's essentially another couple of rules for delta and epsilon.
So there is no intuition.
Just means that if delta A, well, we can write it as Fi tensor Gi, and then we apply epsilon times identity to that. So then we have epsilon Fi tensor Gi, and then we map. So that means just this, that should be A. And the same way we have that A should be equal to this. So like this is still some, I guess, some very heavy restriction on delta and on epsilon. But I'm not sure how intuitive it really is. The only thing I can do, again, is draw the comparison to the flipped case, where we flip all the arrows, because then this basically boils down to 1 times R is equal to R, and R times 1 is equal to R. So the unit rules for our algebra structure. And just like the map that sends 1 to 1 is a unit, the map that sends the map epsilon is what's called a co-unit, and those are called the co-unit laws.
Like, this is like basically some sort of definition for a commutative algebra, right?
Yeah, like it, but yeah, it's basically what I'm getting at now. Definition: a C bialgebra is a triplet R delta epsilon, where we call delta co-multiplication and epsilon co-unit, such that, well, R is a C algebra. So sort of the context we've been in before. Then delta. And to be fair, that's basically just the stuff we've found out so far, is a C algebra morphism epsilon R to C is a C algebra morphism. Then we have the co-associativity law. And then we have epsilon times identity after delta is identity tensor epsilon after delta co-unit law. Yeah.
what is the difference between co-associativity and commutativity?
Well, associativity means that L tensor M tensor N will be canonically isomorphic to L tensor M tensor N.
So commutativity is a special case.
No, commutativity is something completely different.
Okay, I see. But this will obviously satisfy the co-associativity too, right?
Sorry, what?
If it is commutative, it will also satisfy the co-associativity.
No, not necessarily.
Because we can keep flipping, right? No?
Well, commutativity means you can switch the order in which you write things.
Yeah.
Associativity means you can switch the order in which you apply things.
Okay.
Sort of. You first apply this tensor product or this tensor product. And here it's just about exchanging L and M. But I guess the theorem or the big theorem, or not a big theorem, but like the consideration above show that if R is a C bialgebra, then R mod, the category of left R modules or of representations of that bialgebra, is a monoidal category. Meaning that we have tensor products and that these tensor products sort of behave like expected. So I guess the question now is, well, how does this apply to the cases that we already know? The examples of algebras that induce some sort of representations. For example, if G is a group, is the group algebra a bialgebra? And yes, it is. Well, in what way? Firstly, note that if we take the tensor product of the group algebra over C with itself, then this is essentially just the group algebra of G squared, just by basic properties of, I guess, polynomial rings, which makes our definitions a bit easier.
What is G squared exactly?
The Cartesian product of G with itself.
Okay.
So how do we define delta? Well, we can define delta on just one group element, and we define it to be G tensored with itself. This ultimately says that if we have a representation and another representation, and then blah, 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 we have an element. Yeah, then basically we define this tensor product of the representations just by acting on both things individually. Just like in group theory, I suppose, you defined the tensor product of two representations. And secondly, what's our epsilon? Well, epsilon applied to a group element is 1. Yeah, I guess note that this thing here is symmetric. Or you could also say co-commutative. Okay, bye, Marcel. But yeah, delta is symmetric, so I guess R is co-commutative, but note that it is in itself still very much not commutative. And I guess if you wanted to, you could check the co-associativity and co-unit laws, but well, it essentially works.
Can you give us a more like asymmetric example of co-associativity?
Yeah, that will be the very last example I give.
Okay.
Because sort of the things that arise classically are either commutative or co-commutative, and the ones that are neither, those are sort of the interesting cases that all of it was built for, but they are also the ones that are really hard to describe.
Okay.
Yeah, a slightly different example is if G is an affine algebraic group. So for example, the general linear group or the special linear group or the orthogonal group or something like that. And R is its coordinate ring. So the regular functions that are defined on the whole group, then you can, well, the tensor product is then the coordinate ring of, again, the Cartesian product of G with itself. And then you can define delta of some function applied to, well, an element of that thing as f applied to the product of G with G prime, which is sort of where it really becomes obvious that if you sort of have an underlying group, then, sort of motivates the name of co-multiplication, because in a way, you are multiplying at some point. You are at some point using that you are describing a group. And similarly, the co-unit, if we apply that thing to a function, then it's the same as just entering the neutral element into the regular function itself. Yeah, I guess a similar thing could be done for Lie groups, where you then consider the smooth functions on that Lie group. Thing is just you need to work in the correct category of rings, because just taking the tensor product in the category of rings just doesn't give you C infinity of some Cartesian product. So you would need to work a bit harder for that.
This is once again commutative though.
Well, this is now commutative, but not co-commutative. And this makes it sort of dual to this thing here.
What does co-commutative mean exactly?
Co-commutative means that co-multiplication is symmetric. This thing here means, this thing here is commutative because, well, when you're multiplying, you're just multiplying functions. Yeah. So essentially, you're just multiplying complex numbers. So there, the multiplication is symmetric. And this is sort of the second big area where these bialgebras arise, when we have some group that happens to also be some sort of geometric space, and that geometric space is described by some ring of functions. In this case, for simplicity, regular functions. In the Lie group case, that would be smooth functions. And well, we can multiply those functions just because they have, well, scalar functions. They take values in C, but you can also co-multiply them by sort of using the underlying group structure of the geometric space you're looking at. And yeah, and of course the last big example, if we sort of go back to an analogy to the group algebra case, when G is a Lie algebra, then, and this is its universal enveloping algebra, then we can define delta on an element V of that Lie algebra to be V tensor 1 plus 1 tensor V, and epsilon of such an element to be 0. Then this also gives us a valid bialgebra structure, and this essentially amounts to saying that when you take the tensor product of two Lie algebra representations, then an element V of that Lie algebra acting on M tensor N is the same as V acting on the first component, tensored with the second component, plus just V acting on the second component, which is how once upon a time we defined taking the tensor product of Lie algebra representations.
This is the whole SU2 cross SU2 example, right?
This is the whole what example?
The SU2 cross SU2. For like,
not necessarily, but probably.
yeah.
Yeah, and I guess we can also do a more general thing. Let V be a vector space. Then we've seen that the tensor algebra is a ring, it's a C algebra. And yeah, I guess the tensor product of TV with itself is just TV itself. So then we can define delta that just maps V and V to 1 tensor V plus V tensor 1, and epsilon, which maps V to 0, and just extend this. And well, this makes TV into a C bialgebra. And well, by the construction that we did last lecture, we can see that this is just the quotient of this example. So that was the part on tensor products. Shall we maybe take a short break?
Yeah.
Yeah, something I maybe neglected to mention at the beginning. The whole thing we are looking at today can be can be put together in one very nice observation, which is usually referred to as Tanaka duality. Notice that this Tanaka is actually written with 2N, so it's not the very common Japanese name Tanaka. Sorry. It's actually a bit more difficult, but that's just a side note, which is that the structure, or there's a nice correspondence between the structure on R and the structure on the category of R modules. So if we sort of have this nice table, R is a ... and R mod is a ... then we have already seen that if R is a C algebra, then R mod is an abelian category. Then if R is a C bialgebra, so if we have co-multiplication and co-unit, then we can also take tensor products and have trivial tensor products, meaning that this is a monoidal category. And then, which I guess we're going to explore further, if it's a C Hopf algebra, or I guess just a Hopf algebra, then we have a rigid monoidal category. Meaning that we can take tensor products and we can take duals. And if we're working in a finite dimensional realm, we also have an inner Hom and all of those nice things. And lastly, if we have a quasi-triangular Hopf algebra, then the category of modules over that is a braided rigid monoidal category. Or I guess a braided and rigid monoidal category.
What's rigid exactly?
Rigid means that you have duals.
Okay.
Or ultimately that you have Hom, inner Hom, so that you can also equip just the linear maps with the structure of a representation. And braided means that while M tensor N might not be the same as N tensor M, there is at least one map, one isomorphism that relates the two.
This is very similar to what we discussed last class too, right? Like this idea of a degree maybe, or like
degree?
No, like the fact that there always exists this isomorphism and when we're talking about tensor products.
Yeah, okay. When we're talking about tensor products over C, then sure. It's just in this case we're talking about representations.
Yeah.
And
no, I get that.
More complicated. Like, I mean, this whole point here is a bit moot, since like all of the examples I gave are like co-commutative, meaning that like not only is this category braided monoidal, it's symmetric monoidal, but still like there are interesting cases in which this is not a priori a given. Okay, so let's get straight into duals. And no, I don't mean duals in the Galois sense. So for an R module M, we'd like to make M star, which is the linear maps, the C linear maps from M to C into an R module. And we would like two things, namely we would like such that the map M tensor M prime to R. Oh, okay. Yeah, that should be C, right? And the map mapping M star tensor M to C. Yeah, I guess V tensor lambda maps to lambda of V, and lambda tensor V maps to lambda of V. That those two are linear. And we can again. Okay. So how do we do that? Well, after I've again plugged in the power cord for my laptop. So first thing, how do we make this thing into an R module? We could again do something similar to what we did before, like try to work with some kind of ring homomorphism. The thing is, it just won't really, that doesn't really work that well. But we can make do with something slightly different. Let S from R to R be an R, well, not a homomorphism, but an anti-morphism. What does that mean? It means that this thing sends sums to sums, and it sends products to products. But on doing this, it reverses the order. So think of something like, well, taking the inverse of a matrix or taking the transpose of a matrix. Well, okay, the inverse doesn't work at all, but taking the transpose is like a good idea because it preserves sums, but it maps sort of a product to the product with the order reversed. And then define A times lambda. Well, how do we define such a thing? We apply to a vector, and that should just be lambda applied to SAV. And you could ask, why does this define an R module structure? For example, if I do something like this, is that really equal to A times B applied to lambda? And well, since we've chosen S exactly such that it reverses the order when multiplying, that is indeed the case. And yeah, now we just need to derive conditions for our S using the conditions that these two maps here be are linear. And well, we can plug stuff in. Ultimately, it will boil down to to that thing, and yeah, I guess also that thing. What exactly does that mean? It means if we start in R, then split our thing up using the co-multiplication, then apply our map S on one of the two sides, but not on the other. And then we multiply the things again. Or alternatively, if we split up, then apply our map S on the other side, and then multiply again. We should get the same as if we just mapped to C and then included that thing into R again. And yes, here I've used two new symbols that I've recently not used, where eta from C to R is the inclusion, or alternatively, we could call it the unit. And because it maps a complex number to the complex number multiplied with 1, and mu from R tensor R to R is the multiplication. And usually when you read up on things related to Hopf algebras and bialgebras, there's usually a lot of effort involved first writing the algebra laws in terms of these two functions, making them look like the diagrams that we've seen before. I just skipped that because I didn't think it was very instructive. Anyway, we want
basically mu is like our typical module multiplication.
That's the normal ring module multiplication, really.
Okay, normal ring multiplication.
Yeah. Okay, now for the big definition. A Hopf algebra is a tuple H delta epsilon S, where we call delta co-multiplication, as we had before, epsilon co-unit, as before, and S antipode map. Where, well, H delta epsilon is a bialgebra, and S from H to H is a C algebra antimorphism. Such that eta after epsilon is equal to mu after S tensor ID tensor delta is equal to mu after ID tensor S after delta. Well, exactly this beautiful diagram here. Yeah, then we call it a Hopf algebra. And again, we could view this condition as saying just that S behaves in a way like some sort of inverse. What are examples of this? Well, we could look at how we can make the things we've considered before into bialgebras. Sorry, to Hopf algebras. So for, again, a group algebra, we define the antipode map of some element of that group algebra to be, well, it's still supposed to be an antimorphism, so we can pull out the sum, pull out the CI, I suppose, because of this behemoth of a rule. CI S of GI. And how do we define S applied to some element of the group? Well, we just take the one thing of the group that we haven't used yet, the fact that there are inverses. So essentially just S of G is G inverse for G and G. And then basically this law here translates just to the fact that, well, it's the inverse with respect to the co-multiplication. Secondly, in the case of our affine algebraic group, so for regular functions on the group G, define S of f applied to some element of the group, just to be the inverse of that element, inserted into f. Again, note that because we are doing inverses, we are reversing the order in which we would multiply. Then for the universal enveloping algebra, define S of x, where x is in the Lie algebra as minus x. And similarly for the tensor algebra of a vector space, same thing really, for x in V. And then build the continuation of that. Well, what does that mean? Well, it
just one
relates.
question. In these cases, when you wrote it as S of x equal minus x, where is that reversing of the order happening?
Well, we just define it that way. We require that if we then have a product of two vectors, then this is sort of by definition equal to S of y times S of x. And well, if x and y are then actually elements of the vector space, then we can look it up and see that this is minus y times minus x,
Okay.
meaning that on degree 2 elements, it actually just reverses order.
But this is just because like you've defined some sort of inner product here.
That's because we know that sort of UG as a ring is generated by the X in the Lie algebra G. So I can sort of get away with specifying what S does on those generators and then say, yeah, and then sort of take the completion as an anti-homomorphism.
Mm-hmm. Yeah, cool.
So in general, these maps are a bit complicated, but in the sort of easy case where we're just plugging an element in that's generating it inside, we have this easy formula, and otherwise we would have to write just as a sum of products of these generators.
Yeah.
Well, so what's all that about? Essentially, remarks. As I've already said, this way R mod, or I guess when H is a Hopf algebra, H mod is a rigid category, meaning that there are duals, and the things that we defined up here more or less refers to the fact that we can take the dual representation, and for groups we sort of defined the dual representation. Yeah, how did we call that? I don't know. The dual representation was sort of defined as the inverse, but then take the transpose or something like that. In quotes for groups, and then analogously for Lie algebras, I guess it's just tilde or something. I'm not sure what's the symbol that was used. Then it's more like minus rho x transpose. So it is, again, some sort of formalism that generalizes the sort of ad hoc seeming notions of dual representations and what we've done before, tensor product representations. Do I have something else? Okay, so yeah, generally Hopf algebras are what is usually referred to as quantum groups. Sometimes quantum groups mean quasi-triangular Hopf algebras in particular, which are what we are going to talk about next, I suppose. But I guess the original inventor used this terminology, but differently. He used it specifically for Hopf algebras that are neither commutative nor co-commutative. Again, remember that thing here is co-commutative, sorry. That thing here is co-commutative, but not commutative. This thing is commutative, but not co-commutative. This thing is co-commutative, but not commutative. And this thing is also co-commutative, but not commutative. But I guess according to the original definition, all of those are not quantum groups. Although I guess now it is time to discuss the one example of a proper quantum group, namely what is called quantized Sr2. Or the quantized enveloping algebra of Sr2. As you might recall, the universal enveloping algebra of Sr2 is generated by two elements E and F and H, sort of the angular momentum in Z direction, and J plus and J minus if you want. But in this case, we are going to do it a bit differently because it's in fact generated by those three things, subject to some weird conditions, namely that if we sort of conjugate E by K, we get Q squared E. When we multiply, when we conjugate F by K, we get Q to the minus 2 E, and the commutator of E and F is equal to K minus K inverse over Q minus Q inverse, where Q is some number formally adjoined to the complex numbers. And then we can define delta E to be E tensor K plus 1 tensor E. Note that this thing is not symmetric. Similarly, delta F is F tensor 1 plus K inverse tensor F. Delta K is just K tensor K. Then epsilon E is 0, epsilon F is 0, epsilon K is 1, Sk is K inverse, Se is minus E, Sf is minus F. Blah, blah, blah. These definitions give a Hopf algebra over the ring C adjoint Q inverse. Essentially this sort of, yeah, quantized SL2. In a way, this looks a bit like what we would do to SL2 if we set K to 1, sort of. We would get E times 1 plus 1 times E, F times 1 plus 1 times F. Okay, that's sort of how we would define stuff for SL2 itself. Then we have the commutator of E and F is, well, okay, weird stuff, let's not get into that. But then again, co-unit, yeah, sure, makes sense. And the antipode, on one hand, it makes sense to sort of send K to K inverse. On the other hand, E to minus E, yeah, that's also something that seems, yeah, I don't know, I'm not very much familiar to this thing, but it looks like some deformation of SL2.
Like the only thing I don't understand is what is K? Like I just don't understand K.
K is an operator. That's
no, I understand what it is.
Supposed to be a
I mean, like,
stand-in for H, or like the
yeah,
angular
they
momentum
are
in that
deformations, right? Basically deformations to.
Well, the deformation should really be contained in Q, but
Q and K are essentially the same information.
not really, though. I guess K is something like the angular momentum in that direction times Q or something.
Okay.
In any case, there is a great YouTube video about the quantized enveloping algebra that I found recently. That was also given recently, which I will send to you. In any case, last thing, symmetry or braiding, which I guess is the main reason why people consider or why people talk about this. Symmetry, braiding. Yeah, I've already mentioned this, but from what we've done so far, there is no apparent relation so far. No relation between M tensor N and N tensor M. I mean, sure, they are isomorphic as vector spaces. You can just define a map that maps X tensor Y to, Y tensor X. But in general, that map is not R linear, so it's not really what, or I guess H linear now. So it's not really what we want. Or I guess, yeah, only H linear if, well, we can write stuff down and work it out, but essentially if if we reverse the output of delta, then we still get the same, or if delta is symmetric. Tau is in that case just exactly that map, in this case for R tensor R. I guess in that case we call H symmetric or co-commutative. Which is not in general the case. But we can try something slightly different. So suppose R is an element of H tensor H, and we just define a map C from M tensor N to N tensor M, Not necessarily by having by swapping the two things, but by first multiplying them with our element R and then swapping them. So this is a slightly more general notion than just wanting the swapping to be an H linear map. We would still get the same if we chose one tensor one, but maybe one of these will turn out to be what exactly? H linear, which is, yeah, again, a slightly milder condition than wanting tau to be H linear. Let's see, H linear, i.e. And the motivation is, of course, that we want R to be invertible. So then this map C would be invertible. So then they would actually be isomorphic as H modules when R M tensor N and N tensor M isomorphic as H modules, I guess, isomorphic via the map C. And yeah, again, we could can write it out, work it out, and we see that this is the case if R times delta A is equal to tau applied to delta A times R. And if we also want C to be invertible, if conjugation by R is the same thing as swapping those two, as swapping the two tensor things, at least when applying them to elements of the form delta A. Yeah, flipping, I called it. So again, we could ask, what else does C need to satisfy? And there's a bunch of really, really ugly identities. And this is basically playing around with associativity, but essentially wanting this swapping to behave nicely. Essentially, if there's two ways to come from one way to another way, that should more or less be the same. It's what's called the hexagon identities. We want L tensor n swapped one way, then we can apply the associativity. Then we can map with C. This changes the two things, Mn L. Then we can again apply associativity, M tensor N tensor L. Then we can map with identity tensor C. I guess in that direction. We get M tensor L tensor N. Then we can apply associativity again. M tensor L tensor N, and well, this is, we can get to this via that map. That's incorrect. Well, at least it makes sense from whatever. So this is one hexagon identity. There's another one which is basically the same but different, and it's just ugly to write down. And what does this mean? Ultimately, it means that some weird combination of those maps should be 0 or whatever. ultimately means that our R is supposed to play nicely with our co-multiplication. In what way? Well, in that way. And conversely, the other hexagon identity looks like this. Yeah, what are R with those two weird subscripts? Where, well, if we can write R, and this is where stuff gets, where we appreciate that we usually work with functions that combine stuff. Well, if we can write R as some sum like this, sorry, xi, yi, then yeah, notice that R is an element of H tensor H, and then this thing is an element of H tensor H tensor H. And there's basically three ways of mapping an element of H tensor H to H tensor H tensor H, namely by tensoring on the right with 1, by tensoring on the left with 1, or by tensoring in the middle with 1. And those are what I call R12, R13, and R23, basically because the first two tensor components are mapped to the first two, the last two, or the first and the third tensor component there. And yeah, so again, those were our considerations. What kind of definition can we extract from that? An element R in H tensor H is called a universal R element if, or R matrix, I suppose, if this thing is R1, 3, R2, 3, and identity times delta applied to R is R1, 3, R1, 2. Secondly, a Hopf algebra H is called quasitriangular. If it has a universal R element. And then it's usually called a quasi-triangular Hopf algebra, or QTHA. And lastly, a QTHA is called triangular. If it has a universal R element satisfying R inverse is equal to tau of R. Or if we consider this map C, it's basically saying that C applied after C is the identity, or that C is its own inverse. Remark, what does this mean for our category? Well, for a QTHA, define Cm, n for two modules m and n from m tensor n to n tensor m, x maps to tau of r times x. This makes the category of R modules into a braided monoidal category. Meaning that while the tensor product isn't necessarily commutative, we still have some non-trivial isomorphism between the two ways we could write a tensor product, but sort of mapping one way and then mapping the other way doesn't necessarily give you the identity back. However, it does give you the identity back if H is triangular. If H is even triangular, then H mod is symmetric, monoidal. Yeah, and I guess a proposition, a consequence of all of these things are if oof, H is a QTHA, then epsilon times the identity of R is equal to 1. I guess same goes for when I do it the other way. This is probably just a consequence of the unitar laws, the co-unit laws. And secondly, R12 times R13 times R23 is equal to R23 times R13 times R12, which is basically a consequence of those weird hexagon laws here. And this very important equation is called the quantum Young-Baxter equation, or QYBE.
I think this is what Shuvendu's working on.
Yeah, exactly that. So, examples. Ooh, final stretch. So,
No. Before you would go for the final stretch, can you also talk about like deformations and quantizations? Like,
so quantization is basically, instead of looking at the Hopf algebra over C, we're looking at the Hopf algebra over C adjoint Q and Q inverse, I guess, in this case. Or usually you could also say just a power series ring in some formal parameter Q, with the property that when we set Q to 0 or to 1, depending on which flavor of quantization you want to look at, you recover whatever it was you were quantizing. The fact that if you set Q to 1 in this case, you would get SL2 is non-trivial, especially because of this thing here, which would just be 0 if we set Q to 1. But apparently there is some sense in which you can recover the SL2 case from this one, which is why we call it the quantization. And well, deformation is just a more general name for exactly that process.
no, I get that, but what's the implication? Like, these are all Hopf algebras, and in some way, these quantum groups that we're trying to study are like they're different from the Q equal 1 case. Like, what's the difference?
Well, in this case, it's different because it's neither commutative nor co-commutative.
I see.
Unlike U of SL2, which is at least co-commutative.
Yeah.
And this is really the reason why they are called quantum groups, why the word quantum appears in this case. The original motivation was that we can describe groups or some geometric weird groups by Hopf algebras, namely by taking regular functions or by taking the group algebra or something like that, that are either commutative or co-commutative, depending on our construction. But if we were instead considering the class of Hopf algebras that are neither co-commutative nor commutative, then those would describe some abstract notion of a quantum group, just like you use functions to describe classical observables.
I get it.
And then you use non-commuting operators to describe quantum observables. Well, beautiful analogy, even though it's butchered nowadays. Yeah, okay, first example. Well, the things we were looking at before, group algebra, classical enveloping algebra, tensor algebra, they are not only quasi-triangular, they are just triangular. Where we can just take R to be 1 tensor 1. Boring. But there is also an example of, well, where we can put non-trivial quasi-triangular Hopf algebra structures on these things. For example, a non-trivial QTHA structure. Consider G to be the cyclic group with n elements, meaning it's generated by G with the relation that G to the n is equal to 1 again. Let Q be the corresponding primitive root of 1. And then we can define R to be 1 over n times sum of a b from 1 to n, q to the minus a times b, g to the a tensor gb. That thing is invertible. With its inverse being very much the same. Except that we now have a positive sign. And then, well, our delta applied to some element A, R inverse is, well, G really is an abelian group here, so we can just swap stuff around. So this is 1, and this thing is symmetric, so we have that this is equal to that, so done. And it also satisfies this weird stuff. And the other identity, or the other condition, meaning that using this universal R element, we can also turn CG into a quasi-triangular Hopf algebra. And lastly, I guess the one we've all been waiting for, the quantized enveloping algebra. And this one really is a mouthful. And if you want to learn more about this, I really suggest you watch the video that I will send around later. For UQ, SL2, set Q to I believe, again, the nth root of unity. Then what am I doing here? Anyway, we can do some weird R element, define some weird R element by having.
Are you tired, Philip?
I'm a bit tired, yes. But I'm also almost done. So
Yeah, it's the final stretch.
Yep. Times sum from 0 to n minus 1 q minus q inverse to the rth power divided by some weird Gaussian factorial of r times e to the r tensor f to the r, where that Gaussian factorial is defined as product from 1 to r of 1 minus q to the minus t at 2t over 1 minus. Yeah, I probably didn't write this one out nicely, but this basically amounts to q to the minus t minus plus 1 plus every power until q to the 2t minus 1, I believe. Could that be correct? Well, something like that. Anyway, it's like a lot of powers of q summed, t many of them to be correct, and with like steps of 2 or something. Well, never mind. And yeah, one last thing, which I guess is a generalization of what I did here to do this non-trivial QTHA structure. If you have a QTHA, you can twist it. Let H be a QTHA, and chi is an element of H tensor H, invertible with some condition. And epsilon after tensor identity. Chi is identity tensor epsilon applied to chi is equal to 1. Then we can define the so-called Drinfeld twist of this QTHA. Define delta chi to be just delta conjugated with chi, then r chi to be r, well, not really conjugated with chi, but like multiplied with chi and the twisted chi, and then the antipode map, define that to be, well, we can only apply the antipode map on sort of one side to chi. So let's do that, but then also conjugate with that. This whole stuff is just constructed in such a way that H delta chi epsilon s chi r chi is also a QTHA. And that was my last lecture of forbidden maths, I suppose.